Hello everyone, welcome to the first lecture in the course Theory of Computation. In this lecture we will be starting a new topic, and the topic is regular expressions. So till now we have seen many languages, and we have also seen certain kinds of strings accepted by languages. And till now the way we have represented those strings were just using simple English language. Now what are regular expressions? Regular expressions are used for representing certain sets of strings in an algebraic fashion. So instead of simply representing them as we used to do now, these regular expressions are used in order to represent our strings in an algebraic fashion. So before we learn more about regular expressions, there are certain points or rules that you must remember. Let's see what they are. In certain sets of strings in an algebraic fashion. So instead of simply representing them as we used to do now, these regular expressions are used in order to represent our strings in an algebraic fashion. So before we learn more about regular expressions, there are certain points or rules that you must remember. Let's see what they are. Okay, so these are the rules or points that we must remember about. They are regular strings till now. These regular expressions are used in order to represent our strings in an algebraic fashion. So before we learn more about regular expressions, there are certain points or rules that you must remember. Let's see what they are. Okay, so these are the rules or points that we must remember about regular expressions. So let's see the first point. Any terminal symbol, that is symbols that belong to sigma, including the empty and the null symbol, are regular expressions. So till now we have seen many symbols like a, b, c, and so on, which we use for representing the inputs and outputs. So all all these symbols, known as terminal symbols, including the empty and the null symbols, are all regular expressions. So that is what the first point says. Now let's see the second point. The union of two regular expressions is also a regular expression. So let's say that we have two regular expressions which we call R1 and R2. These two are regular expressions, and then the union of these regular expressions, which is represented by R1 plus R2. This is also a regular expression. So if R1 and R2 are regular, then the union will also be regular. Alright, so let's see the third point. The concatenation of two regular expressions is also a regular expression. So let's say we again have two regular expressions, R1 and R2. Then the concatenation of these two regular expressions, which is represented by R1, R2, or we may put a dot in between them. So this will also be a regular expression. So if we have two regular expressions, then the concatenation will always be a regular expression. Alright, so let's come to the fourth point. The iteration or closure of a regular expression is also a regular expression. So if we have a regular expression, let's say R, and then the closure of R, which is represented by R star, will also be a regular expression. So what is this closure? I've already mentioned and discussed about this closure in one of our previous lectures, but let me just repeat it again. Suppose we have a symbol A, and then the closure of A represented by A star will be everything that you can form using this A. So it includes the empty symbol as well as A and A, and so on. Everything that you can form using this A will be an infinite set. So that is the closure of A. So if A is a regular expression, then its closure will also be a regular expression. So that is what this fourth point is telling us. And then the fifth point says that the regular expression over sigma are precisely those obtained recursively by the application of the above rules once or several times. So all the regular expressions over sigma, what are they? They are simply the regular expressions that are obtained by applying the these rules which are given above once or many times. So we see that when we have regular expressions, if you do the union of them or concatenation of them or closure of them, you obtain new regular expressions. So this fifth point tells us that the regular expressions over sigma are those which are obtained by applying these rules which are given above once or many times. So these are the rules that we need to remember about regular expressions. So in the next lecture we will in the last lecture, we have studied about regular expressions, and in this lecture, we will be seeing some examples of regular expressions. We will see how to form regular expressions from some given sets. Alright, so here we have the question that is to describe the following sets as regular expressions. So here we have 5 sets given here, and these are just written like this, means the elements of these sets are mentioned. And instead of just writing like this, we will see how can we describe these sets in the form of a regular expression. Alright, so let's see the first one. The first one is a set containing the symbols 0, 1, and 2. That means it could contain anything from 0 or 1 or 2. These are the things that can be contained in this set. So in the form of regular expression, it can be written like this. Let's say the regular expression is R equal to 0 or 1 or 2. So this first symbol is used to denote or. So 0 or 1 or 2. So these are the things that can be contained in this set, and this is the regular expression that is used to denote this. So it was simple. So let's come to the second one. Here we see that the empty symbol and AB. These are the only symbols present in this set. So this will be denoted like this. R equal to the empty symbol and AB. So we see that here when the empty symbol was not included, when we had more than one element, we use the plus symbol to denote. But here when you only have one symbol and the empty symbol along with it, you don't have to use the plus or symbol, you can just write empty symbol and AB. So these are the only things that will be, you can just and the empty symbol along with it. You don't have to use the plus or symbol, you can just write empty symbol along with it. You don't have to use the plus or symbol, you can just write empty symbol and AB. So these are the only things that will be accepted or that is present in this set, and this is the regular expression that is used to describe this. Alright, so I have it here. So let's come to the third one. In the third one, we have the symbols ABB, A, B, and BBA. So this means that it can be anything like ABB or A or B or BBA. So any of these symbols can be present in the set, or a language that contains this, any of these symbols will be accepted. So how do we write the regular expression? It's very simple. Just write, since there is a or here, we just have to use the plus symbol. ABB or A or B or BBA. So this is how you can write the regular expression for this set. Alright, now let's come to the fourth one. So here we see the empty symbol, then 0, 0, 0, 0, 0, 0, and so on. So what is this? I've already explained this in the last lecture if you remember. If you look carefully, you find that these are any strings that can be formed by using the 0 symbol, 0, 0, 0, 0, 0, or any more symbols that can be formed by putting together any number of zeros that you want. So all the strings that can be formed using 0 along with the empty symbol, it denotes the closure of 0. So this is the closure. This is the closure of 0. So how do we denote 0? It denotes the closure of that symbol. So this is 0 closure. Alright, so let's come to the last one. Here we have 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. So this also means any strings that can be formed by using this symbol 1. So we can put any number of 1s together, and whatever you form is the set here. So is this the closure of 1? This looks like the closure of 1, but this is not the closure of 1. Why? We can call it a closure only when all the strings that can be formed by the symbol along with the empty symbol is included. But here we see that the empty symbol is not included, so we can call this a closure. So instead you denote it like this, R equal to 1, and instead of a star like this, we denote it with a cross symbol. So this denotes the closure of a symbol excluding the empty symbol. So this is how we denote it when the empty symbol is not present. So I hope this was clear to you. This is how we describe in this lecture, we will be seeing some of the identities of regular expressions. So these identities of regular expressions are important when you solve some problems related to regular expressions. And also if you are given some exams like these identities are important because sometimes you get direct questions based on these identities. Alright, so let's get started. So here, the first one says that phi plus r equal to r. Now what does this mean? So here, phi is used to denote an empty set. So that means if you do the union of phi and r, where r is any regular expression, then you get back the regular expression r. So plus is used to denote union. So the union of phi and any regular expression is the regular expression itself. Alright, that's simple and straightforward. So let's come to the second one. So here it says phi concatenation r union r concatenation phi is equal to phi. That means if you concatenate an empty set phi with a regular expression, and if you also concatenate a regular expression with an empty set phi, and you perform the union of them, then what you get is an empty set phi. Alright, so now let's come to the third one. Here it says epsilon r equal to r, epsilon equal to r. So in the last lecture we have used this symbol to denote epsilon, but let's know that this symbol and this symbol is also used to denote epsilon. So here it says that if you perform the concatenation of epsilon and any regular expression r, or the same thing, if you perform the concatenation of r and any epsilon symbol, then what you get is r itself, the regular expression. Alright, let's see the fourth one. The fourth one says epsilon closure equal to epsilon. So this is very simple. If you have epsilon and if you perform the closure of that, then what you get is epsilon itself. And this is important. This says that the closure of phi is not phi, but it is epsilon. So if you have phi and if you perform the closure of this phi, then you get epsilon symbol. Okay. Now let's come to the fifth one. This is very simple. Union of two regular expression is a regular expression. R plus R equal to R. That's very simple. Okay, so now let's come to the sixth one. The sixth one says R star equal to R star. So this means that if you perform the concatenation of the closure of two regular expressions, then you get the closure of that regular expression as a result. So we have two regular expressions, similar ones R and R, and we take the closure of them, and then we do the concatenation of them. Then what do we get? We get R star. Okay, and next is the seventh one. This says that R star equal to R star R. So this basically just means that you can write it in this way or this way. Concatenation of R and its closure is equal to the closure of R concatenation R. So that is what it means. Let's come to the eighth one. This says that R star and the whole of its star equal to R star. That means you have the closure of the regular expression, and if you perform the closure of it again, then what you get is the closure of the regular expression itself. Okay, now let's see ninth one. This is important. Here it says epsilon plus R star, which is also equal to epsilon plus R star R equal to R star. Now what does this mean? Here you see that we have R star and here we have R star R. So we already proved in number 7 that these two are the same. So what does this R star mean? So this R star means this is the closure of R, and if you concatenate it with R, what you get is R plus. So I've already explained what is R plus in the previous lecture. So R plus means the closure excluding the epsilon symbol. Okay, so here we get the R plus. That means the closure excluding the epsilon symbol. Now we are doing the union of the epsilon symbol. That means you're adding the epsilon symbol to that. So if you add the epsilon symbol to R plus, then what do we get? We get closure of R. I'm going to explain to you because R plus was closure excluding epsilon. So if you just add epsilon to it, you get the closure. Okay, so now let's come to the 10th one. Here it says that P concatenation Q and the whole of its closure concatenation with P is equal to P and then the whole concatenation of Q and P its closure. So this is something you just have to remember it. Okay, so now let's come to the next one. Here it is also you have to remember it. It says that P plus Q whole closure is equal to P closure concatenation Q closure and its whole closure, and it is also equal to P closure union Q closure and its whole closure. Okay, and then the last one says P plus Q concatenation R equal to P R plus Q R. So you can remember it this way. Here you have union of P2 and here you have concatenation of R. So it is just like multiplying this R inside. So here you get P and this R, PR, and this plus is written over here, and then Q and this R, QR. So this is the way you can remember it. And also the same way R concatenation with P plus Q, and P union Q is equal to R P plus R Q. Here also you can just remember like you're multiplying it inside R and P plus then R and Q, R Q. So this is just a way to remember it. So these were some of the important identities of regular expressions that you have to remember. So I will just give it to you. Thank you for watching and see you in the next one. In this lecture, we will be studying about Arden's theorem. So this Arden's theorem is important when you deal with regular expressions, and it says that if P and Q are two regular expressions over sigma, and if P does not contain epsilon, then the following equation in R given by R equal to Q plus RP has a unique solution, that is R equal to Q is that as stated by the Arden's theorem. So here, this is what we get. Whole thing, Q plus, if we take out Q common, then we take out Q common, now what do we get? Here we get epsilon plus P square plus goes on Pn plus P star Pn plus 1. Till now we have completed the identities of regular expressions, and we have also studied Arden's theorem, and in this lecture we will be trying to prove a regular expression that is given here. So it says that prove that this is equal to this. So these are two regular expressions, and the first one is 1 plus 0 0 star 1 plus 1 plus 0 star 1 0 plus 1 0 star 1 star 0 plus 1 0 star 1, and we have to prove that this is equal to 0 star 1 0 plus 1 0 star 1 and the whole star. Okay, so how do we do this? We first take the LHS. So the LHS is equal to this one. So let me write this down. 1 plus 0 0 star 1 plus 1 plus 0 0 star 1 0 plus 1 0 star 1 the whole star and 0 plus 1 0 star 1. Okay, so now if you see here, you see that this term 1 plus 0 0 star 1 is repeated here, 1 plus 0 0 star 1. So we see that here we have this term, here also we have this term. So what I can take this as a common. So let me take this as common. 1 plus 0 0 star 1. I take it as common. So if I take it as common, what do I get? Here, once it's taken as common, this becomes epsilon and plus. So this is taken out over here, and these two terms are remaining. So let me write these two terms 0 plus 1 0 star 1 star and 0 plus 1 0 star 1. Okay, now if you look at this expression, you see that these two terms are the same. 0 plus 1 0 star 1. Here also it is 0 plus 1 0 star 1. And over here we have a star. Now if you recall the identities that we have studied, we have already studied that epsilon plus R star R is equal to R star. Right, where R is in regular expressions. So here, if you consider this as R, you see that it is like R star R. So this whole thing can be replaced by 0 plus 1 0 star 1 whole star. If we consider this as a R, so we'll do that now. So I'll take this down as it is 0 star 1, and this whole thing can be replaced by only this much star using this identity that we have already learned. So I can write 0 plus 1 0 star 1 whole star. Okay, now we are left with these two expressions. Now what I will do is here I will write epsilon into 1 plus 0 0 star 1, and this term will be decided as it is 0 plus 1 0 star 1 star. Now why did I do this? I have this term I just written down here, and I've added an epsilon symbol. And this is another identity that we have studied. Epsilon R is equal to R. If you just have epsilon before R, that is still equal to R. We have studied this identity before, so I'm applying it here. I'm just putting epsilon before this expression. So even if I put an epsilon here, it is still equal to this. So I can write this as this one. Okay, now after I write this, from this expression, I'm going to take out epsilon and 0 0 star as common. Epsilon plus 0 0 star, I'm taking it as common. Epsilon plus. In this lecture, we will be seeing some examples of designing regular expressions. So we have a question given here that is to design a regular expression for the following languages over AB. So here our sigma or our inputs are AB. So we'll be designing the language over AB. And then the first one is a language accepting strings of length exactly 2. And the second one is a language accepting strings of length at least 2. And the third one is a language accepting strings of length at most 2. Okay, so let's do the solution over here. Let us first do the first one. So let's say this is language L1, and this is a language that should accept the strings of length exactly 2. So if our alphabets are AB, what will be the strings of length exactly 2? The possibilities are AA, AB, BA, and BB. So these are the only strings that will be accepted in this language L1. So how do we design the regular expression for this? It's very easy. we can just write AA plus AB plus BA plus BB. Just do the union of all the strings that are possible in this set. And we can further simplify this. We can take out A common from these two terms. If I take out A common, I get A plus B over here. And plus from here, from these two terms, we can take out B as common. So we'll get A and B again. A plus B. So this A plus this B, let me write them together. So this will be A plus B and these two A plus B. So this is a simplified form, and this regular expression gives us the language that accepts the strings of length exactly 2. Now you see that when it is exactly 2, we are having A plus B and again A plus B. Now if you want to design a language that accepts strings of length exactly 3, then you can give one more A plus B here. Or if you want of length exactly 4, you can give another A plus B again, and it can be designed further in that way. Now let's do the second one. So the second one is a language accepting strings of length at least 2. So what is the meaning of at least 2? At least 2 means it could be AA, AB, BA, BB. These are the strings of length 2, and it says at least 2. At least 2 means 2 or more than 2. So it could be AAA, and it could continue. This will actually be an infinite set because it says at least 2, which means 2 or more than 2. 2 is the minimum one, and the maximum is not specified, so it is an infinite set. So how can we write this? The regular expression for this can be written as R equal to A plus B. And again, I'll write A plus B. Why did I write this? This is because we already found out from this first question that A plus B and A plus B, this is used to represent the strings of length exactly 2. So now I have made this for exactly 2, and then this should be at least 2. So this is exactly 2, and here I will write A plus B star. Now what does this mean? This means that 2 or more than 2. And why is that? Here we are making sure that strings of length 2 will be there for sure. So this term over here is used to denote anything that will be more than length 2. So if you want it to be of length 2, you can just replace this star with 0. So this term will be cancelled, and you will have only these 2, and it will be of length 2. If you want it to be of length 3, you can give 1 over instead of star, so you will have A plus B, A plus B, A plus B. And if you want length 4, you can give power 2 over here. So it can accept any strings of length 2 or more. That means at least 2. So minimum is 2, maximum is not specified. Okay, so now let's come to the third one. The third one is language accepting strings of length at most 2. Now what is the meaning of at most 2? At most 2 means maximum it should be 2 and minimum is not specified. So minimum we can have nothing, null, that is epsilon, and then we can also have strings of length 1 like A and B. And also you can have strings of length 2, AA, AB, BA, and BB. Now these are only strings. Why? Because it's at most 2, maximum is 2, so these are the ones with length 2, and we cannot have 3 or anything more after that. So these are only strings that will be accepted by this language. So how do we write the regular expression for this? And then AB. Now you can simplify this and write it as B plus it to be of length discard this A because this A over. Or if you want A, B, you can take the string regular expression this one. Images. So this is how we design the regular expressions for these given languages. So I hope this video. Thank you for watching, and see you in the next one. In this lecture, we will be seeing another example of how to find the regular expression for a given NFA. So if we see here, we have an NFA given. Now task is to design the regular expression for the given NFA. So in order to do this, what we have to do is we have to write the equations for each of the states of this NFA, and after doing that, we have to put the equations of all the states to the equation of the final state, and that will give us the required regular expression for the given NFA. So let's become clear when we solve it, and let's see how we can do this. So here we see that we have 3 states. Q1, Q2, and Q3, where Q1 is the starting state and Q3 is the final state. So first of all, let us write the equations for the states that I was talking about. So first of all, expression for the given equations for each of the states of the we have to do regular expression for the given NFA given. Now task is to design the regular expression for the given NFA. So in order to do this, what we have to do is we have to write the equations for each of the states of this NFA, and after doing that, we have to put the equations of all the states to the equation of the final state, and that will give us the required regular expression for the given NFA. So let's become clear when we solve it, and let's see how we can do this. So here we see that we have 3 states, Q1, Q2, and Q3, where Q1 is the starting state and Q3 is the final state. So first of all, let us write the equations for the states that I was talking about. So first of all, let's check for the final state, that is Q3. So how do we write the equation for this? In order to write the equation for any state, check what are the incoming transitions to that state. So here we see that this is incoming transition to Q3. It is coming from Q2 with an input A. So since it's coming from Q2 with an input A, we write it like this. And check if there are any more incoming transitions to Q3. There are none. So this is only one, and this one, let me call it equation number 1, that is equation for Q3. Okay, now let's do the same thing for state Q2. In Q2 we see that Q2 has incoming transitions from Q1 and also from Q2 and also from Q3. So we have to write all of them. We have to do the union of all of them. So let's see how we can do that. From Q1 it is coming with an input A, from Q1 it is coming with an input A, plus from Q2 it is coming with an input B, Q2 input B, plus from Q3 it is coming with an input B, Q3 B. So this one I call equation number 2, and this is equation for state Q2. Now let's do the same thing for state Q1. So what are the incoming transitions? Here we have this transition coming to Q1. So this transition that comes from nowhere, that will be called epsilon. Plus we have incoming transition from Q1 itself, Q1 with input A, Q1 with input A, plus from Q2 it's coming with input B, Q2 with input B. So there are no more incoming transitions. So this will be equation number 3, and this is for state Q1. So now we have written the equations for states Q1, Q2, and Q3. And now what we have to do is we have to simplify these states. So first let's take equation number 1, and that is state Q3. Q3 is equal to Q2A, and we can substitute the value of Q2 from this equation number 2. So Q2 can be written as Q1A plus Q2B plus Q3B, and this A can be written as this. And now let me simplify further by taking this A inside. So Q1AA plus Q2BA plus Q3BA. So let me call this equation number 4. Alright, so let's do the same thing for equation number 2. That is the state Q2. So Q2, how will we write it? Q1A plus Q2B plus Q3B. So this is the equation for state Q2. Now what we have to do, let us simplify this. And how do I do this? What will I do is, here we see that we have Q1, Q2, and Q3. So what I will do is that this Q3 over here, I will substitute it with the value of Q3 from equation number 1. So let me write here, putting value of Q3 from equation number 1. So what do I get? Q1A will remain the same, Q1A plus Q2B also will remain the same, and Q3 can be written as Q2A. Q2A, that is from equation number 1, and B as it is. Now let us simplify further. Q1A plus Q2B plus, I take this B inside, so this becomes Q2AB. Now if you see that we have this Q2 and Q2, 2 times there are Q2, so I can take out Q2 common from this. So equal to, so this is Q2 equal to Q1A plus, let me take out Q2 common from here. So if I take out Q2 common, I get B here plus AB. Okay, so now if you check this equation is of the form R equal to Q plus RP, where Q2 is R and Q1A is Q, and this Q2 is R as we said, and this B plus AB, this whole term is P. And then if you remember the Arden's theorem that we have studied in the previous lecture, we saw that whenever we have an equation of the form R equal to Q plus RP, it can be written as R equal to QP star. This is by Arden's theorem. So if you have not studied Arden's theorem, you can refer to the previous lectures. So this equation is of the form R equal to Q plus RP, so I can write it in the form R equal to QP star by following Arden's theorem. So let me write it here, R is Q2 and QP star. What is Q? Q1A and P star, and P is B plus AB. This whole term is P, B plus AB star. So this I will call equation number 5. So we have solved Q2, we have simplified Q2. Now let us take our equation 3, which was Q1. equation 3 was q1. So you see this one q1 over here. So let us write it over here. Q1 equal to epsilon plus q1a plus q2b. Now I'll try this. In this lecture, we will see another example of finding the regular expression for the given DFA. So here we have another DFA given, and then we have to find the regular expression for this DFA. So here we see that we have states q1, q2, q3, and q4, where q1 is the initial as well as the final state, and then we have inputs a and b. So I've already explained the steps to find the regular expressions from DFA in the previous lecture, so here we will just solve it. So first of all, what we have to do is we have to write the equations for each of the states. So let's start with q1, which is our initial as well as final state. So how do we write? First, check what are the incoming transitions to q1. So this is incoming transition coming from nowhere, so this is written as epsilon plus, and here we see that from q2 there is incoming transition with input b. So we can write q2b plus, and then from q3 also there is incoming transition to q1 with input a. So I have to write q3a, and then there are no more incoming transitions. So this is the equation for q1, and then we call it equation number 1. Now let's do the same thing for equation number 2. That is for q2. So in q2 we see that there is only one incoming transition, that is from q1 with input a. So we can write it as q1 with input a, and there are no more incoming transitions to q2. So this is equation number 2. Now let's do the same thing for q3. So for q3 also we see that there is only one incoming transition, that is from q1 to q3 with input b. So since it's starting from q1, I will write q1 input is b. So this one we call it equation number 3. And let's do the same thing for q4. So in q4 we see that there are incoming transitions from q2, q3, and also from q4. So let me first write the one for q2. q2 it comes with input a plus, from q3 it is coming with input b, q3 b, and for q4 it is coming with both input a and b. So we have to write q4 with input a plus q4 with input b. So this is equation number 4. Okay, so now we have written the equations for all the states. Now let's try to take this final state and try to simplify it. Final state is q1. So that is equation number 1. I take, and that is q1, and what is q1? Epsilon plus q2b plus q3a. Now we see that we have q2 and q3 over here, and this q2 and q3's values can be substituted from equations 2 and 3. So let me put the values. So I'm right here putting values of q2 and q3 from equations 2 and 3. So how can we write this? q1 equal to this epsilon will be as it is, epsilon plus. Now q2 can be written as q1a, and this b can be written as b itself, plus q3 can be written as q1b, and this a I write it as a itself. Okay, so now we get this, and from here I see that I have q1, so I can take out q1 common. So epsilon plus, let me take out q1 common. So what do I get? I get ab plus ba. Now if you observe this equation, q1 equal to epsilon plus q1 ab plus ba, we can see that this equation is of the form r equal to q plus rp, where this q1 is r and this epsilon is q and q1 is r as we said, and this whole term over here, this is p. So this can be written as r equal to qp star by Arden's theorem. So whenever you have an equation of the form r equal to q plus rp, can be written as r equal to qp star by Arden's theorem. So this is of that form. So let me write it in this form. So r is q1 and qp star, q is epsilon, and in this lecture, we will be seeing another example of designing regular expressions for the given DFA when there are multiple final states. Till now, we have seen how to design the regular expressions when there are only one final state in the DFA, but here we see that in this DFA there are two final states. So we'll see how will we find the regular expressions for this kind of DFAs where there are multiple final states. So the process is very simple. We have to find the regular expressions for all the final states that we have, and at the end we have to just do the union of them. So let us proceed as we used to normally do. First, we'll find the equations for the states that we have here. So here we have states q1, q2, q3, and q1 and q2 are the final states. So let's first start with state q1 and make the equation for q1. q1 can be written as, see the incoming transitions. We have one incoming transition coming from nowhere, which can be represented by epsilon, plus there is incoming transition from q1 itself with input 0. So q1 is 0, and there are no other incoming transitions to q1. So this is the equation for q1, and then this will be equation number 1. And let's do the same thing for q2. In q2 you see that there is incoming transition from q1 with input 1. So q1 1 plus there is incoming transition from q2 itself with input 1. So we write q2 1, and then there are no more. So this will be equation number 2. That is for q2. Now let's do the same thing for q3. For q3 we see that there are incoming transitions from q2 as well as from q3. So from q2 is coming with input 0. So q2 0 plus from q3 is coming with inputs both 0 and 1. So q3 is 0 plus q3 1. So that's all for q3, and this is equation number 3. Okay, so now we have made the equations for all the states that we have. So now we see that q1 and q2 are both final states. So first of all, let's take one of the final state and find the regular expression for that. So let me start with final state q1. First, let me start with this. For I will take equation number 1, that is for the equation for q1. So q1 equal to epsilon plus q1 is 0. So this is my equation. And if you see this equation, we see that this is of the form r equal to q plus rp, where this q1 is my r, and this epsilon is q, and this q1 right here, this is also r as we said, and this 0 is the p. So whenever you have an equation of the form r equal to q plus rp, it can be written as r equal to qp star from Arden's theorem. This is from Arden's theorem. And so let me write it in this form. So this is r equal to q plus rp, so I can write it in this form. So I write r, which is q1, equal to qp star. Q is epsilon, and p star, what is p? 0, 0 star. And also we know from identities that epsilon into r is equal to r itself. So here we have epsilon into 0 star. So here my 0 star is the r. So epsilon into 0 star will be 0 star itself. So here I get the regular expression for my final state q1. So let me just call this equation number 4. Alright, now we have finished solving for final state q1. But we know we have one more final state, which is final state q2. So q2 is also a final state. So we have to find the regular expression for q2 as well. For that I use equation number 2, which is the equation for q2. So q2 is equal to this one. q1 1 plus q2 1. Alright, now we see that we already found the value of q1 to be 0 star. So I'll substitute this value of q1 in this equation. So this will be equal to q2, and q1 can be replaced with 0 star, and this one can be written as 1 itself, plus q2 1. And how do we get this? This is by putting value of q1 from equation number 4. Okay, now we see that this equation is also of the form r equal to q plus rp. How? This q2 will be r, and this whole term 0 star 1 will be q, and this q2 right here, this is my r as I said, and this one over here, this will be p. So this can be written as r equal to qp star by Arden's theorem. So let me write that. So r is q2 equal to qp star. So what is q? 0 star 1, and p star. So what is p? P is 1. So 1 star. So we are getting this. So this is the regular expression for the final state q2. So we have two final states q1 and q2. So when we have two final states, the regular expression will be the union of both the final states. The first final state was q1, whose expression we got to be 0 star. So when we write 0 star, union means plus. The second final state was q2, and we got the expression as 0 star 1 1 star. So this can be written as 0 star 1 1. Here I put 1 1 star. Okay, and also in identities we studied that epsilon plus r star is equal to r star. We studied this in our identities, if you remember. So here we see that epsilon plus 1 1 star. So if you treat 1 as regular expression r, so this whole thing can be written as 1 star. So 0 star, and this whole thing can be written as 1 star from this identity that we have already studied. So now when we perform the union of both the final states, the resulting regular expression that we get is the required regular expression for the DFA. So whenever you have more than one final state, find the regular expression for all the final states and perform the union of them. That will give you the regular expression for the DFA. So I hope this was clear to you. Thank you for watching. See you in the next one. till now we have studied how to design regular expressions for a given dfa, and in this lecture we will be studying about conversion of regular expressions to finite automata. That means, given a regular expression, how do we convert it to its equivalent finite automata? Alright, so in this lecture we will be studying some of the important rules that we should remember while we convert regular expressions to finite automata, and from the next lecture onwards we will be seeing some examples. Alright, so let's get started. So we know that in regular expressions we have expressions of many forms, and let's say that we have inputs a and b, and you have an expression of the form a plus b. That means a union b, which you already know. So if you have an expression of this form a plus b, how do we draw or design the finite automata for this? So if you have the expression of the form a plus b, we need to have two states. Let me call them states a and state b, and I can say that a and we need to find a function of this form a. We have expressions of many forms, and let's say that we have inputs a and b, and you have an expression of the form a. Let's say that we'll be seeing some examples. Alright, so let's get started. So we know that in regular expressions we have expressions of many forms, and let's say that we have inputs a and b, and you have an expression of the form a plus b. That means a union b, which you already know. So if you have an expression of this form a plus b, how do we draw or design the finite automata for this? So if you have the expression of the form a plus b, we need to have two states. Let me call them states a and state b, and I can say that a will go to the next state b when it gets input small a, and also a on getting input small b also it will go to the next state b. Or we can also express it in this way. You can write a and b, and instead of using two transition lines, just one line you can represent like this, a or b. So this means that a union b, that means a or b. So the state on getting either input a or input b, it can go to the next state, that is b. So this is the same thing represented here, just using one transition line. A on getting either input a or input b, it can go to the next state b. So whenever you have a regular expression of this form, this is how you will design the finite automata for that. Alright, so let's see another expression. There's another expression that we have here in our regular expressions of this form, a dot b, or just represented as just ab. So when you have expressions of this form, you need to have three states, a, b, and c. And we can say that a will go to the next state b on getting input small a, and b will go to the next state c on getting input small b. So here, unlike this, where it will go to the next state of either a or b, in this case it's not like that. In this case, it will go to the next state on getting the first input a, and it will proceed to the next state again when it gets the next input b. So when you have expressions of the form ab, you have to specify two different transitions for those inputs a and b, unlike this one. Alright, so this is how you do it when you have this kind of expression. Okay, now we can see another expression that is a star, closure of a, which we have already studied. So if you have expressions of this form, the way we represent it is very simple. Take a state and let it go to itself on getting that input a. So this means that closure of a means any number of a's. So here, any number of a's, any number of a's you can get in this kind of state that you design. So these are three important rules which you should remember while we will be designing the finite automata from the given regular expression. So if you get this form, a union b, this is how you design it, and if you get a and b like this is the way you design it, and if you get closure of any input, this is the way you have to design it. So keeping these rules in mind, we will be seeing examples from the coming lectures. In the last lecture, I have taught you the rules that we need to remember for converting regular expressions to their equivalent finite automata. So in this lecture, we will be using those rules, and using those rules, we will be trying to convert these given regular expressions to their equivalent finite automata. Okay, so let's get started. So here we have three expressions, and we'll start with the first one. The first one, it says b a star b. So this means that the strings that will be accepted in this regular expressions are strings like b, b. This means that it should have b followed by zero or more number of a's, which is a closure, and then followed by b again. So here, this b means there is no a in between, just bb. It will also be b a b, that is one number of a, then b a a b, and so on. So we need to design the finite automata for this. So I already told you when the symbols are separated by and. So what we need to do, let me make a state. Let me say we have one state which is state a, which will be my starting state, and I have another state here, state b, and I have another state here, state c, and c will be my final state. And I'll say that this starting state a goes to the state, starting state, the state. Let me say we have one state with two. So I already told you when the symbols are separated by and. So what we need to do, so I already told you when the symbols are separated by and. So metaphor this. So I already told you when the symbols are separated by and. So what we need to do, let me make the symbols are separated by and. Finite automata for this. So we need to design the finite automata for this. So I already told you when the symbols are separated by and. So what we need to do, let me make the states. Let me say we have one state which is state a, which will be my starting state, and I have another state here, state b, and I have another state here, state c, and c will be my final state. And I'll say that this starting state a goes to b when it gets the input small b. Alright, and then this b will go to the next state, that is state c, when it gets the next input this b. Alright, so we have made for this b and this b. Now what about this a? How shall we make for this a? I will make a self loop to this b itself when it gets the input small a. So I've already told you in the previous lecture, whenever we have AND operations, we have to make states for each of the inputs. So here we have b and b here. They go to a goes to b on getting input small b, and b will go to the next state c when it gets the next input small b. And whenever you have a closure of any symbol, you have to make a self loop. So here we have made a self loop in this state b. So let's check if these strings are accepted by this finite automata bb. So starting from a, when b comes to this b, when the next b comes to state c, which is the final state. So this is accepted. Now b a b, b a b, again comes to the final state. This is also accepted. b a b, b a, another a, and then b comes to the final state again. This is also accepted. So now we have successfully designed the finite automata for this regular expression b a star b. Okay, now let's go to the second one. So the second one says a plus b, and then followed by a c like this. So here we have a union or a plus operation, and here we have an AND operation. So in this case, what shall we do? I already told you in the previous lecture that whenever you have a plus symbol, you can treat it as a or. So let's say I have a state a, which is my starting state, and I have the next state which is state b, and then a can go to the state b on getting input small a, in the symbol on both inputs small a and small b. And now we have the next input c, and this will proceed to the next state, which will be my final state c for this regular expression. So let's see what are the strings that are accepted by this regular expression over here. So a plus b and c. So that means a or b followed by a c. It could be a followed by a c, or it could be b followed by a c. So these are the kind of strings that will be accepted by this regular expression. So let's see if this is accepted by this automata that we have created. A c comes to the final state, this is accepted. B c, d c comes to the final state, this is accepted. So we have successfully designed the finite automata for the regular expression a plus b and c. Alright, so we are done with that. Now let's come to the next one over here, number 3, which is a, and in bracket I have b c star. Okay, so before we design the finite automata for this, let's see what are the kind of strings that are accepted by this regular expression. So this means that a and b c closure. That means a followed by a number of b c. This group b c can be 0 or more. So it may be like a just by itself, because I said b c could be 0 or more. So if b c is 0, then it could be just a, or it could be like a b c, and it's one b c, or let's say a b c b c, right? Two b c's, or a b c b c b c. Three number of b c's. So these are the kind of strings that will be accepted by this one. So let's see how we can design the finite automata for this. So I'll start with a state which I will call state a, which will be my starting state or initial state, and I'll make another state here b, and I'll say that a will go to the next state b on getting input small a. Okay, so we're done with this part. Now I need the closure of bc. So in order to make the closure of bc, I will make another state here which I will call state c, and I will say that from state b it will go to c on getting input small b, and from c it will go back to state b on getting input small c. And here what will be my final state? I will make b as my final state. Now why did I do this? This is because we see that whenever we reach bc, whenever c is the last symbol, that is when the string is ending, or that is the strings that will be accepted. So here we see that when it gets input small b, it comes to c, but c is not a final state. But when it gets input small c, see like here, it goes to b, which is a final state. And also the string a by itself also be accepted. That is why it comes to this final state b when it gets input small a. So let's just check if this string is accepted or not. A by itself, it comes to the final state b, is accepted. A b c. So a b and c again comes to the final state, accepted. A b c b c. A b c again b c, accepted. A b c b c b c. A b c b c b c. So any number of b c's that you have, it will be accepted. So now we have also designed the finite automata for this regular expression. So this is how you convert the regular expression to the equivalent finite automata, and we will see more and bigger examples in the coming lectures. So thank you for watching, and see you in the next one. In this lecture, we will be seeing another example of conversion of regular expression to its equivalent finite automata. So here we have a regular expression given, and our task is to convert it to its equivalent finite automata using the rules that we have studied in the last lectures. Okay, so let's get started and see how we can do this. So starting with the first sequence, we have A or B, and it's for closure. So this symbol over here is same as the plus symbol that we used to use, which is not or. So I am using these different symbols because I don't want you to be confused when you see these different symbols. I want you to know that this plus and or just means the same. So first of all, let's try to make the finite automata for this sequence A or B is for closure. Okay, so let me take a state which I will call state number 1, and let me make this the starting state. And if you see that this is a closure, so whenever we have a closure, what we do is we make a self loop. That is what we have studied. Now when we go to this state on either A or B, so on either A or B, it will go to now state which I will call state number 1, and for this sequence A or B is for closure. Okay, so let me take a state which I will call state number 1, and let me make this the starting state. And if you see that this is a closure, so whenever we have a closure, what we do is we make a self loop. That is what we have studied. Now when we go to this state on either A or B, so on either A or B, it will go to this state 1 itself. Okay, so now we have completed the A or B closure part. Now let's come to this part. Now if you see here, you see that after the sequence, it's like an and it is followed by A, B, B, or A plus B, and now to B. So on either A, and let me make this the starting state. And if you see that this is a closure, so whenever we have a closure, what we do is we make a self loop. That is what we have studied. Now when we go to this state on either A or B, so on either A or B, it will go to this state 1 itself. Okay, so now we have completed the A or B closure part. Now let's come to this part. Now if you see here, you see that after the sequence, it's like an and it is followed by A, B, B, or A plus B. And this plus is not a plus in between A and B, but it is a plus over this A, and we'll see what it means. So first let's do this part A, B, B. So for that, let me make another state over here, which I will call state number 2. And we already studied that whenever we have sequence of the form A, B, B, that means there is no plus in between, it is just written together like this. That means you just have to make separate states for them and make them keep moving forward. So from here, the state 1 will go to state 2 on getting input A, that is this A over here, and then I'll make another state over here, which is state 3, and I'll send this state 2 to state 3 on getting input B, which is this B over here, and there's one more B, but I will make another state which I will call state 4 over here, 2 and state move like this. That means you just have to make separate states for them and make them keep moving forward. So from here, the state 1 will go to state 2 on getting input A, that is this A over here, and then I'll make another state over here, which is state 3, and I'll send this state 2 to state 3 on getting input B, which is this B over here, and there's one more B, but I will make another state which I will call state 4, and state 4 will also be a final state because this is a terminating symbol, and this 3 will go to state 4 on getting the next input B. Now we have completed this part A, B, B, and followed by this we have an OR symbol, which is followed by A plus B. Now whenever you have an OR symbol, you have to continue from the state where you started. Now here this is the state from where we started, this A, B, B, and since it is an OR, this also will be followed from this same state itself from where this was started. Okay, so let me make another state here which I will call state number 5, and I will send this 1 to 5 on getting input A. Now we have a design for this A plus. Now what is the meaning of this A plus? A plus, if you remember when I told you the identities, I told you it means one or more number of A's. So it could be A, and it would go on. Now what is the difference between A plus and A closure? In A closure, it can also include the empty symbol and followed by any number of A's. So the difference is that in A closure, there could be 0 or more number of A's, but in case of A plus, it will be 1 or more number of A's. It means at least one A should be present. So as we design for this A plus over here, what we do is in the state number 5, I give a self loop and I put A over here. Now if you look at the state 5, which is for this A plus, we see that it will come to state 5 only on getting at least one A. It will come at least on one A, and after that it could get any number of A's. So we make sure that at least one A will be present, followed by any number of A's if required. So we have successfully made the automata for this A plus. Now it's followed by a B. So there is nothing in between, it is just written together. So for this B, I just make another state which I will call state 6, and since that is also the ending symbol, so this will be a final state, and this 5 will go to this state 6 on getting the input B. So that is for this one. So for this A plus, we have designed this, and for this B here, we have this part. So now we have successfully made the final automata for this regular expression. And if you look at this final automata, we may be thinking whether it is a DFA or an NFA. So if you look carefully, we can find that it is an NFA. So we see if you look at state 1 on getting input A, it has moves to 1, 2, and 5. It's having more than one moves. And also if you look at state number 2, you see that it goes to state 3 on getting input B, but it does not have any move on input A. So all these things are properties of NFA. So you see that these are NFAs that we have designed, and it is obviously possible to convert this to its equivalent DFA. So if you want to convert a regular expression to its equivalent DFA, so first design its NFA like this using the process that we have done here, and then after you convert it to its equivalent DFA using the conversion of NFA to DFA method that we have already studied in the previous lectures. So I hope this was clear to you. Thank you for watching, and see you in the next one with another example. In this lecture, we will be seeing another example of conversion of regular expression to its equivalent finite automata. So here we have a regular expression given, and we will convert this to its equivalent finite automata. So since this is a long one, what we'll do is we will try to break it down as small parts, and then we will design it in a simple way, and then we will keep expanding it till we get the required finite automata. Alright, so here you see we have 1, 0, and we have a plus symbol, that is 4, and we have this sequence that follows. So what I will do is, for my first step, I will treat this 1, 0 as a single symbol, and 0 plus 1, 1, and 0 closure 1, this whole thing I will treat it as another symbol. So let us design it in a simple way like that. So for that, I will take a state over here, which will be my starting state, and I have another state here, which will be my final state. So I will have only two states over here for the beginning, and since this is one symbol, this is another symbol, and they're separated by a plus. So whenever they are separated by a plus, I will default to just send them to the next state using just two different transitions. So this will go to the next state on getting input 1, 0, and then this will also go to the next state on getting the input, and they're separated by a plus. The state here, design in a simple way like that. So for that, I will take a state over here, which will be my starting state, and the first step, I will treat this 1, 0 as a single symbol, and 0 plus 1, 1, and 0 closure 1, this whole thing I will treat it as another symbol. So let us design in a simple way like that. So for that, I will take a state over here, which will be my starting state, and I have another state here, which will be my final state. So I have only two states over here for the beginning, and since this is one symbol, this is another symbol, and they're separated by a plus. So whenever they're separated by a plus, I will default to just send them to the next state using just two different transitions. So this will go to the next state on getting input 1, 0, and then this will also go to the next state on getting the input 0 plus 1, 1, 0 star 1. So since we are getting this as a single symbol, we are writing like this. Okay, so we have written like this, but we don't just leave it like this because this is not a proper finite automata. We have to further expand this. So let's expand this part. So I'll take this initial state that we created, and here we see that this is 1, 0. There is no plus symbol in between them. It is 1 followed by 0. Now when you go to when there is symbols of this form, when the symbols just follow each other, so what you have to do is you have to make separate states for each symbol and make them proceed. So here I'll make one state, and this will be the minus state which we already had, and here I'll send this state to the next state on getting input 1, this one, and then from here I will send it to this state, that is the next state, on input 0, which is this 0. So we expanded this and we have created a automata like this. Now coming to this part, what we'll do is we'll make states for these symbols as well. So first let's look at this part, 0 or 1, 1. So whenever you're separated by a or, what you have to do, you have to just make a single state and then send them both to that state. So I'll make a state over here, and I'll send this to this state on getting input 0, this 0, and or 1, 1. That means even on getting input 1, 1 also, it should come to this state. So 1, 1. Okay, so we're done with this part, and then we have 0 star and 1, and this one is of this form. That means there's no plus symbol in between them, so we have to make two separate states for them. So let me make a state here. This state is already there. So from this state, I will send it to the next state on getting input 0 star, and from this state, it will go to the final state or the next state on getting this input 1 over here. Okay, so we have designed this part also. Now it's still not complete because we see that here we have two symbols and here we have 0 closure. We have to expand this further. Only after that we can get the final result. So let me expand it over here. We have our starting state, which is this one, and this part will be the same. We have go to states over here. So this will go to this state, and this state will go to this state on getting input 1 and 0. Alright, so let's expand this. So here we see that we have 1, 1. So when we have symbols of this form, I told you we have to make two separate states for the symbols. So let me make a separate state over here, and this state will come as it is over here like this, and I'll say this will come to this state on getting input 1, and it will proceed to the next state on getting the next input 1. So we have designed for these two, and this 0 it will remain the same. It has to go to this state, which is this one. So I will send this state over here on getting input 0. Okay, so now we are done with this part. We have expanded this, and we have got states like this. Now what we have to do is we have to do the zero closure. Now I already told you whenever you have a closure, what you have to do is very simple, just send a self loop. So I'll send a self loop to this state, and I will give it input 0. So this is what we are going to do for zero closure, and we are done with that. After that, we have this one following it. So it will follow from here going to the final state. So from here we will send it to this final state on getting the input 1. Now we see that there is only one input symbol associated with each transition, so we have successfully designed the automata for this expression. And if you want, you can give names for these states that we have made here, like you can call it A, B, C, D, and E. So this is how you design the finite automata for the given expression by designing it in a simple way and then expanding it further to get the required finite automata for the given expression. So I hope this was helpful. Thank you for watching, and see you in the next one. In this lecture, we will be studying about equivalence of two finite automata, which means that given two finite automata, how do you recognize or how do you identify whether these two given finite automata are the same or not? And what do we mean by same equivalent? By same equivalent, we mean that the two automatas perform the same kind of function. That means the languages they accept will be the same. So that is what we are going to study. And in order to identify whether two automata are equivalent or not, there are certain steps that you need to follow in order to identify them. So first, let's see what are those steps. So here are the steps that are required to identify the equivalences. So the first step is for any pair of states qi and qj, the transition for input a belongs to sigma is defined by qa to b, where the transition from qi on a goes to qa and the transition from qj on a goes to qb. The two automata are not equivalent if for a pair qa qb, one is intermediate state and the other is final state. So what we mean by this is that suppose we have two automatas, and from the two automatas we select pairs of states, one from the first automata, the other from the second automata, and let's say we get a pair qi qj, and then let's say we have input a which is there in both automatas, and we will see the transition of these pairs on getting the input a. That means where does this qi from the first automata go to on getting input a, and where does the state qj from the second automata go to on getting this particular input a. And let's say that qi goes to qa and qj goes to qb on getting this input a in both the automatas. And then if qa and qb are both final states or both non-final states or intermediate states, then we can say that the two automatas are equivalent. That means when you get this pair qa qb, if you see that both qa and qb are either final states or either non-final states, then the two automatas are equivalent. But if you see that qa is an intermediate state, that means qa is a non-final state and qb is a final state, that means if one is an intermediate state and the other one is a final state, then the two automata are not equivalent. So that is what this steps are trying to tell us. So this will become more clear when we take example. And then the second step says that if initial state is final state of one automata, then in the second automata also initial state must be final state for them to be equivalent. That means in the first automata, if its initial state and final state is the same state, then even in the second automata, its initial state and final state should be the same for them to be equivalent. Otherwise, they will not be equivalent. So let's take a simple example to understand this in a better way. Okay, so here we have an example where we have two automata. This is the first automata and this is the second automata. So let me call them by names. Let me say that this is A and this is automata B. So in order to check whether these two automata are equivalent or not, I will make a table over here where here I will write the states, where I make a pairs of states over here, and you notice in this automata the inputs are C and D. So here I write for input C and here I write for input D. Okay, so if you notice that in automata A and B, in A the initial state is Q1 and the final state is also Q1. And even in this automata number B, Q4 is the initial state as well as the final state. So here also initial state and final state is the same. So we satisfy this second condition already, where it says that if the initial state is final state in one of them, it should be the same for the other as well. So since in both of them the initial state and final states are same, so the second condition is already satisfied. Now let's check the first condition. So for that we have to make pairs of states. So here let's make the first pair as Q1 and Q4 since they are the initial states. Let me make a pair like Q1, Q4. So we have to see where does this Q1 and Q4 go on getting input C and D. So let's see Q1 on input C. Q1 on input C goes to Q1 itself, and Q4 on input C goes to Q4 itself. So here we get a pair of state Q1, Q4, and check if Q1 and Q4 are final states or intermediate states. So we see that Q1 is a final state and Q4 here is also a final state. So let me just write Fs to just represent it as a final state. So both of them are final states. Okay, now let's do for input D. Q1 on input D goes to Q2, and Q4 on input D goes to Q5. And let's check if they are final states or intermediate states. So if you see Q2 is not final state or intermediate state, so I write I as intermediate state, and Q5 is also an intermediate state. So we see that this pair both are final states and this pair both are intermediate states. So this was the condition that we wanted. This is the condition that was mentioned in step 1. If both of them are final states or if both of them are intermediate states, then we can say that they are equivalent. But if one is a final state and the other is an intermediate state, then they cannot be called equivalent. Okay, but this is not complete because we already checked for one pair. We have to check for all the pairs of states. Alright, now let's check for the pairs Q2 and Q5. Q2, Q5. You check for Q2, Q5. Q2 on input C goes to Q3, and Q5 on input C goes to Q6. You can check it in the diagram. And if you see that Q3 is an intermediate state, and Q6 is also an intermediate state over here. And let's do the same thing for input D. Q2 on input D goes to Q1, and Q5 on input D goes to Q4. And if you check, you can find that Q1 and Q4 both are final states. So here we again get pairs which are same. Either they are both intermediate, or they are both final states. So far they are equivalent. Now we have to check for the next pair of states, which will be Q3 and Q6. Q3, Q6. So if you check for Q3, Q6, we see that Q3 on input C goes to Q2, and Q6 on input C goes to Q7. And let's see where they are intermediate states or final states. Q2 is an intermediate state, I guess, and Q7 is also an intermediate state. Alright, now let's do the same thing for input D. Q3, this Q3 on input D goes to Q3 itself, and Q6 on input D goes to Q6 itself. You can check in the diagram, and we see that both Q3 and Q6 are also intermediate states. So far also all the pairs that we got are either both intermediate states or both final states. So now it is equivalent. Now if you see that we have compared Q1 and Q4, Q2 and Q5, Q3 and Q6, but Q7 is left, and we see that Q2, Q7 is a new pair of state that has been formed in this table. So you have to check for the pair Q2, Q7. So let's check for this pair. To check for this pair, we see that Q2 on input C goes to Q3, and Q7 on input C goes to Q6. And if you see Q3 is an intermediate state, and Q6 also is an intermediate state. So right, I guess. And then on input D, where do they go? They go to Q1, Q4. And Q1 and Q4, if you check in our diagram, Q1 and Q4 are both final states. So these two are also final state, final state. Okay, so now you see that for all the pairs that we have checked, the transitions or the pairs of state that we get on input C and D are both final states or both intermediate states. Here final state, here intermediate state. So we see that all the pairs are the same kind, either they are final state or intermediate state. So if you find that all the pairs are either final state or intermediate state, then we can say that the automata A and B are equivalent. Are equivalent. Now when you are checking, if you find that if in any of the pairs one is a final state and another is an intermediate state, then at that moment you can stop the checking and confirm that they are not equivalent. But from this example, we found that both these automata are equivalent. To identify the equivalences. So the first step is for any pair of states Qi and Qj, the transition for input A belongs to sigma is defined by Qa to B, where the transition from Qi on A goes to Qa and the transition from Qj on A goes to Qb. The two automata are not equivalent if for a pair Qa Qb, one is intermediate state and the other is final state. So what we mean by this is that suppose we have two automatas, and from the two automatas we select pairs of states, one from the first order matter, the other from the second order matter. And let's say we get a pair qi qj. And then let's say we have input a which is there in both order matters, and we will see the transition of these pairs on getting the input a. That means where does this qi from the first order matter go to on getting input a, and where does the state qj from the second order matter go to on getting this particular input a. And let's say that qi goes to qa and qj goes to qb on getting this input a in both the order matters. And then if qa and qb are both final states or both non-final states or intermediate states, then we can say that the two order matters are equivalent. That means when you get this pair qa qb, if you see that both qa and qb are either final states or either non-final states, then the two order matters are equivalent. But if you see that qa is an intermediate state, that means qa is a non-final state and qb is a final state, that means if one is an intermediate state and the other one is a final state, then the two order matter are not equivalent. So that is what these steps are trying to tell us. So this will become more clear with the example. And then the second step says that if initial state is final state of one order matter, then in the second order matter also initial state must be final state for them to be equivalent. That means in the first order matter, if its initial state and final state is the same state, then even in the second order matter, its initial state and final state should be the same for them to be equivalent. Otherwise, they will not be equivalent. So let's take a simple example to understand this in a better way. Okay, so here we have an example where we have two order matter. This is the first order matter and this is the second order matter. So let me call them by names. Let me say that this is A and this is order matter B. So in order to check whether these two order matter are equivalent or not, I will make a table over here where here I will write the states, where I make a pairs of states over here, and you notice in this order matter the inputs are C and D. So here I write for input C and here I write for input D. Okay, so if you notice that in order matter A and B, in A the initial state is Q1 and the final state is also Q1. And even in this order matter number B, Q4 is the initial state as well as the final state. So here also initial state and final state is the same. So we satisfy the second condition already, where it says that if the initial state is final state in one of them, it should be the same for the other as well. So since in both of them the initial state and final states are the same, so the second condition is already satisfied. Now let's check the first condition. So for that we have to make pairs of states. So here let's make the first pair as Q1 and Q4, since they are the initial states that we make. Okay, like Q1, Q4. So we have to see where does this Q1 and Q4 go on getting input C and D. So let's say Q1 on input C. Q1 on input C goes to Q1 itself, and Q4 on input C goes to Q4 itself. So here we get a pair of state Q1, Q4, and check if Q1 and Q4 are final states or intermediate states. So we see that Q1 is a final state and Q4 here is also a final state. So let me just write Fs to just represent it as a final state. So both of them are final states. Okay, now let's go for input D. Q1 on input D goes to Q2, and Q4 on input D goes to Q5. And let's check if they are final states or intermediate states. So if you see Q2 is not final state or intermediate state, so I write IS just below intermediate state, and Q5 is also an intermediate state. So we see that this pair both are final states and this pair both are intermediate states. So this was the condition that we wanted. This is the condition that was mentioned in step 1. If both of them are final states or if both of them are intermediate states, then we can say that they are equivalent. But if one is a final state and the other is an intermediate state, then they cannot be called equivalent. Okay, but this is not complete because we have already checked for one pair. We have to check for all the pairs of states. Alright, now let's check for the pairs Q2 and Q5. Q2, Q5. If you check for Q2, Q5, Q2 on input C goes to Q3, and Q5 on input C goes to Q6. You can check it in the diagram. And if you see that Q3 is an intermediate state, and Q6 is also an intermediate state over here. And let's do the same thing for input D. Q2 on input D goes to Q1, and Q5 on input D goes to Q4. And if you check, you can find that Q1 and Q4 both are final states. So here we again get pairs which are same. Either they are both intermediate or they are both final states. So far they are equivalent. Now we have to check for the next pair of state, which will be Q3 and Q6. Q3, Q6. So if you check for Q3, Q6, we see that Q3 on input C goes to Q2, and Q6 on input C goes to Q7. And let's see where they are intermediate states or final states. Q2 is an intermediate state, I guess, and Q7 is also an intermediate state. Alright, now let's do the same thing for input D. Q3, this Q3 on input D goes to Q3 itself, and Q6 on input D goes to Q6 itself. You can check it in the diagram, and we see that both Q3 and Q6 are also intermediate states. So far also all the pairs that we got are either both intermediate states or both final states. So till now it is equivalent. Now if you see that we have compared Q1 and Q4, Q2 and Q5, Q3 and Q6, but Q7 is left, and we see that Q2, Q7 is a new pair of state that has been formed in this table. So you have to check for the pair Q2, Q7. So let's check for this pair. To check for this pair, we see that Q2 on input C goes to Q4. If you see that we have compared Q1 and Q4, Q2 and Q5, Q3 and Q6, but Q7 is left, and we see that Q2, Q7 is a new pair of state that has been formed in this table. So you have to check for the pair Q2, Q7. So let's check for this pair. To check for this pair, we see that Q2 on input C goes to Q3, and Q7 on input C goes to Q6. And if you see Q3 is an intermediate state, and Q6 also is an intermediate state. So right, I guess. And then on input D, where do they go? They go to Q1, Q4. And Q1 and Q4, if you check in our diagram, Q1 and Q4 are both final states. So these two are also final state, final state. Okay, so now you see that for all the pairs that we have checked, the conditions for the pairs of state that we get on input C and D are both final states or both intermediate states. Here final state, here intermediate state. So we see that all the pairs are the same kind, either they are final state or intermediate state. So if you find that all the pairs are either final state or intermediate state, then we can say that the automata A and B are equivalent. Are equivalent. Now when you are checking, if you find that if in any of the pairs one is final state and another is intermediate state, then one will even stop checking and confirm that they are not equivalent. But from this example, we found that both these automata are equivalent. So this is the steps that we follow, and I hope it's clear to you by in this example. So see you in the next lecture with another example. In the last lecture, we have studied about equivalence of two finite order matter. We have studied how to find out whether two given order matter are equivalent or not. So in this lecture, we will see one more example in which we will try to find out whether two given order matter are equivalent or not. So if you have not watched the previous video, I suggest that you watch it first, where I have explained the steps that you have to follow for the procedure in detail. Okay, so here we have two order matter given, and we call them A and we call this B, and our task is to find out whether these two order matter are equivalent or not. So if you see here in order matter A, Q1 is the initial state as well as the final state, and also in order matter B, Q4 is the initial state as well as the final state. So this satisfies one of our condition. So one of the condition for equivalence was that if in one of the order matter the initial state and final state is the same, then even in the other order matter the initial state and final state must be the same for them to be equivalent. So this condition is satisfied in this example. Okay, and then the other condition was that for every pair of states, the pairs of state that is generated on a particular input should be either both final states or both intermediate states. Then they will be equivalent. So let's check that condition. So for that we make a table over here. So here I'll have the pairs of state, seems to be for my states, and you see in this order matter the inputs are C and D. C in the other input symbols that we have C and D. Okay, now let's take the pairs of states. So here the initial states are Q1, Q4. So let's make a pair of state Q1, Q4. So this is a pair of state, and let's see where does this state pair go on getting input C and D. So Q1 on input C, it goes to Q1 itself, and Q4 on input C goes to Q4 itself, Q4. So this is a pair of states that we get, and if you notice Q1 and Q4 are both final states. So let me write final state. This is also final state. So if you find that the pairs that we obtain are both final states, then they are equivalent. So far we are finding that these order matters are equivalent. Okay, so let's see what happens on getting input D. Q1 on getting input D, it goes to Q2, and Q4 on getting input D goes to Q5. So let's check if these states are final states or intermediate states. Q2 is intermediate state, Q5 is also intermediate state. That means non-final state. So here also the pairs of states that we get are both the same kind of states. That means they are both intermediate states. So this condition also supports the fact that they are equivalent. So far we are finding that they are equivalent. Now let's take the next pair of states, which will be Q2 and Q5. Q2, Q5. And let's see where they go on getting input C and D. Q2 on input C goes to Q3, and Q5 on input C goes to Q7. And what kind of states are these states? Q3 is an intermediate state or non-final state, and Q7 is also an intermediate state. Okay. Now let's see where do they go on getting input D. Q2 on input D goes to Q1, and Q5 on input D goes to Q6. Q6. And let's check what kind of hairstyle is. We see that Q1 is a final state, it is a final state, whereas Q6 is a intermediate state. Okay, so in this way we are getting one state to be a final state and the other to be an intermediate state. So whenever we get this kind of condition where one is final state and the other is intermediate state, this condition proves and shows that the two given automata cannot be equivalent. So this condition shows that automata A and automata B are not equivalent. Now there are more cases that we can check, but we don't have to check because from this condition shows that they are not equivalent, and we can just be sure and write that A and B are not equivalent. So whenever we get this kind of conditions, we can be sure that the two given automata are not equivalent. So this is an example of two automata which are not equivalent, and we found them out using this procedure. So I will just leave you, thank you for watching, and see you in the next one. In this lecture, we will be studying about pumping lemma for regular languages. So what is a pumping lemma? Pumping lemma is used to prove that a language is not regular. So I already taught you in previous lectures what are regular languages and what are non-regular languages. So regular languages are the languages that can be represented or designed using a finite state machine. So all languages can be designed using finite state machines, and we know the properties of finite state machines, and we also know their limitations. And due to their limitations, there are some languages that cannot be designed using finite state machines, and those languages are known as non-regular languages. So how can we prove that a language is not regular? Non-regular limitations. And we know the properties of finite state machines, and we also know their limitations. And due to their limitations, there are some languages that cannot be designed using finite state machines, and those languages are known as non-regular languages. So how can we prove that languages are not? This also know their limitations. And due to their limitations, there are some, and we also know their limitations. And due to their limitations, there are some languages that cannot be designed using finite state machines, and those languages are known as non-regular languages. So how can we prove that a language is not regular? So for that, we will be using this pumping lemma. So a pumping lemma is used to prove that a language is not regular. But you should keep in mind that pumping lemma can be used to prove that a language is not regular, but it cannot be used to prove that a language is regular. It can only be used to prove that a language is not regular. Okay, so now we'll see what does the pumping lemma state and how can it be used to prove that a language is not regular. So here, this is the statement of the pumping lemma given, and it says that if A is a regular language, then A has a pumping length P such that any string S where the length of S is greater than or equal to P may be divided into three parts S equal to X, Y, and Z such that the following conditions must be true. Okay, so let's try to understand the statement before we come to the conditions. So it says that if A is a regular language, suppose we have a language which is A, and we assume that it is a regular language. So if A is a regular language, then A must have a pumping length P. It will have a pumping length P such that any string S where the length of S is greater than or equal to P may be divided into three parts. So if you take any string S where the length of this string S that we take from this language A is greater than or equal to the pumping length, then this string S can be divided into three parts, which is X, Y, and Z. That means we take a string S, which belongs to the language A, and we divide that string S into three parts, X, Y, and Z. So you have to decide how you have to divide the string into three parts, and you have to divide in such a way that the following conditions must be true. And what are the conditions? X, Y raised to I, Z belongs to A for every I greater than or equal to 0. That means you have the string S, and now you have it divided into three parts, X, Y, and Z. And if I decide S string S and it'll have a pumping length P such that any string S where the length of S is greater than or equal to P may be divided into three parts. So if you take any string S where the length of this string S that we take from this language A is greater than or equal to the pumping length, then this string S can be divided into three parts, which is X, Y, and Z. That means we take a string S which belongs to the language A, and we divide that string S into three parts, X, Y, and Z. So you have to decide how you have to divide the string into three parts, and you have to divide in such a way that the following conditions must be true. And what are the conditions? X, Y raised to I, Z belongs to A for every I greater than or equal to 0. That means you have the string S, and now you have it divided into three parts, X, Y, and Z. And let's say that the first part X and the last part Z we keep as it is, and this middle part of the string that is Y. The middle part of the string Y, maybe anything, may be some sequence of some kind of symbols. So this middle part Y, if you increase it n number of times, I greater than or equal to 0. That means if you increase this middle part n number of times, and then the string that you obtain after increasing this Y part n number of times must also belong to A, that is a language. Alright, and the second condition says that the length of Y should be greater than 0, and the third condition says that the length of X and Y together must be less than or equal to P, and Y is P, which is the pumping length. So for the language to be regular, these three conditions must be true. So this is what we get from the pumping lemma. And how are we going to prove that the language is not regular using this statement that we have here? Let's see that. To prove that the language is not regular using pumping lemma, follow the below step. Get from the pumping lemma. And so for the language to be regular, these three conditions must be true. So this is what we get from the pumping lemma. And how are we going to prove that the language is not regular using this statement that we have here? Let's see that. To prove that the language is not regular using pumping lemma, follow the below steps. And these are the steps that we are going to follow in order to prove that the language is not regular. And the proof that we are going to do is using contradiction. Okay, so first of all, let's say that we have a language which we call A, and we are going to prove that A is not regular. For that, what we do, since it is going to be proved by contradiction, we first assume that A is regular. So after we assume that A is regular, we already read in the statement of pumping lemma that if A is regular, it has to have a pumping length. So let's say that it has a pumping length, and we call it P. Now, all strings longer than P can be pumped. That means all the strings whose length is greater than or equal to P can be pumped. We already saw in the statement of pumping lemma. Now, what we have to do is we have to find the string S in the language A such that the length of S is greater than or equal to P. Now we are going to take a string S. You have to choose a string S from the language A such that its length is greater than or equal to the pumping length. After that, what you have to do is you have to divide S into three parts: X, Y, and Z, like we already saw in the pumping lemma statement. So you divide the S that you chose from the language A into three parts: X, Y, and Z. Now you have to show that X, Y raised to I, Z does not belong to A for some I. So in the statement for pumping lemma, we saw that if X, Y raised to I, that means this middle part Y, how many other time you increase it, the resultant string that you obtain, X, Y raised to I, Z, must belong to A if the language is regular. So we will show that when you increase the number of this Y part, middle part, and the string that you obtain as a result of X, Y raised to I, Z does not belong to A. The resulting string that you obtain does not belong to the language A. Okay, and then you consider all ways S can be divided into X, Y, and Z. So we have to find out all the ways in which you can divide this string S into three parts: X, Y, and Z, and we show that none of these can satisfy all the three pumping conditions at the same time. So these three conditions that we saw here, we should show that it cannot be satisfied all at the same time. So once you show that these three conditions cannot be satisfied all at the same time, then it shows that S cannot be pumped, which is a contradiction, because if A is regular, then it should be able to be pumped. Now, since it cannot satisfy all three conditions, it is a contradiction to the statement that A is regular. So we prove that A is not regular, and using pumping lemma we prove that A is not a regular language. So I will just say to you, don't worry if it seems a little confusing right now. Just try to understand the theoretical portion in this section. We will take an example in the next lecture where we will be following all the steps and we will try to prove that a language is not regular. So once we get the example, it will become more clear to you. So this is the theoretical part of pumping lemma that we need to understand. I will just read to you. Thank you for watching, and see you in the next one with an example. In the last lecture, we are studying about pumping lemma, where I told you that pumping lemma is used to prove that a language is not regular. So in this lecture, we will see an example where we have a language given, and we will prove that this language is not regular using pumping lemma. Alright, so if you have not watched the previous lecture, you watch first because I described all the rules of pumping lemma in that lecture. Okay, so here we have a language given, which is A is equal to A raised to N, B raised to N for all N greater than or equal to 0. So we have proved that this language is not regular. So I taken this example slightly in one of our previous lectures, and I already told you why this language is not a regular language. This is because this language is of the form A raised to N, B raised to N, which means that we can have any number of A's, and followed by that, we should have the same number of B's like the number of A's that we had. And why this is not regular? It is because in order to achieve this language, we need to keep account of how many A's did we have. Then only we can can repeat that same number of b's. But we know that finite state machines cannot keep count of anything. So this cannot be designed using finite state machines, and all languages that cannot be designed using finite state machines are said to be non-regular. That cannot be designed using finite state machines are finite state machines only with block A and A is language exist. So we have proved that this language is not regular. So I taken this example slightly in one of our previous lectures and already told you why this language is not regular language. This is because this language is of the form A raised to n, B raised to n, which means that we can have any number of A's, and followed by that we should have the same number of B's like the number of A's that we had. And why this is not regular is because in order to achieve this language, we need to keep account of how many A's we have. Then only we can repeat the same number of B's. But we know that finite state machines cannot keep count of anything. So this cannot be designed using finite state machines, and all languages that cannot be designed using finite state machines are said to be non-regular. Okay, so let's get rid of the noise that we have, but we need to have a proof for that. So for proving that, we will use our pumping lemma. Okay, so let's see how we can prove this. So we have the proof here. For that, let's just refer to the rules of pumping lemma that we studied in the previous lecture. So here we have the rules of pumping lemma. So it says that if a length is regular, then it needs to have a pumping length, let's say p, such that any string whose length is greater than or equal to p may be divided into three parts x, y, and z, such that all these three conditions should be satisfied. So I've already discussed this in the last lecture, so I will not be discussing this again. So let's go straight to the steps that we need to follow in order to prove this. So in order to prove a language is not regular using pumping lemma, the following steps are to be followed. First of all, we assume that A is regular. So we assume that the language is given is regular, and if A is regular, then it has to have a pumping length which we will call p, such that all strings longer than p can be pumped. And after that, we will take a string s such that its length is greater than or equal to p, and we will divide it into three parts x, y, and z. So let us do that. So the first step is to assume that A is regular. So we assume that A is regular. Now, if we assume that A is a regular language, then it needs to have a pumping length. It needs to have a pumping length, and let me call the pumping length p. So we have a pumping length p such that any string whose length is greater than or equal to p should be able to be pumped. Now let me choose a string which I will call s, and let's say that s is equal to a raised to p, b raised to p, where p is the pumping length. A language of this form. So again, I'm taking p, which is the pumping length. Now what was the next step? We need to divide this into three parts. What are they? X, y, and z. Alright. Now let's see how can we divide this into three parts x, y, and z. So for now, let me just assume that my pumping length p is equal to 7. So if my pumping length is equal to 7, so I can write this string s. How can I write it? I can write s is equal to, I can write this is equal to y and z. So for now, let me just assume that my pumping length is equal to 7. So if my pumping length is equal to 7, so I can write this string s. How can I write it? I can write s is equal to 1, 2, 3, 4, 5, 6, 7, a 7 times, followed by 1, 2, 3, 4, 5, 6, 7, b also 7 times. Okay, now let's assume that this is our string, which has a pumping length of 7. Now let's see all the possible ways in which we can divide this s into three parts x, y, and z. So for that, let me take first case, case number 1. So the case number 1 is that the y part, that is this y, is in the a part. What do I mean by this? You will be clear when I do this. So what I mean by this is, let's say we have like this 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. Okay, so this is my string, and the y is in the a part. So what I mean by this is, let's assume that y is this one. This part is y. Alright, so this is y, this will be x, and the remaining from here to the end, this will be z. Okay, so this is the first case. So we have divided into three parts x, y, and z, and then the y part, the middle part, is in the a part, means it contains 4 a's. A is 4 a's. So this is how I can divide it in one way, and there is another way we can divide. How is that? Let's say case number 2. Case number 2 says that the y is in the b part. The y is in the b part. Alright, so what do I mean by this? Let's say we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So now I'll divide it in such a way that the y is in the b part. For that, let me take these 4 from here. Okay, this is my y, and then this whole part, this is x, and this one will be z. So y contains only b. That is the case number 2. Now case number 3. There's one more case that we can have. Case 3, it says that the y is in the a as well as b part. Now how is this? I hope you already guessed it. It is like this 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now for the y to be in the both a and b part, I will choose this to be my y. 2 a's from here, 2 b's from here. This is y, and this is x, and this is z. So y has both a and b. So this is case number 3. So these are the three possible ways in which we can divide our string into three parts x, y, and z. Okay, now what do we have to do? Let's just go back and look again. So we divided s into x, y, and z. Now we have to show that x, y raised to I, z does not belong to a for some I. So let's do this. Okay, so coming to the first case, let me draw a line here, and let's do this. First sum to show that x, y raised to I, z does not belong to a for some I. So let's do this. Okay, so coming to the now we go back and look again. So we divided s into x, y, and z. Now we have to show that x, y raised to I, z does not belong to a for some I. So let's do this. Okay, so coming to the first for some x, y, the y is in the b part. Alright, so what do I mean by this? Let's say we have 1, 2, 3, 4, 5, 8. Now it says that the part is like this 1, 3, 4, the this both a and by our we have to look at z. Now we have to show that x, y raised to I, z does not belong to a for some I. So let us do this. Okay, so coming to the first case, let me draw a line here, and let's do this case number 1. So for the first case, let's take any x, y, I, z. So here let me take my I to be 2. That means x, y square, z. That means I have to repeat my y part twice. So this is the first case I'm looking at. So what is my x? X is a, a. And what is my y? Y contains 4 a's. 1, 2, 3, 4. And I have to do it twice. That means again I have to repeat y. 1, 2, 3, 4. Alright, then z. Z contains 1 a and 7 b's. 1 a and 1, 2, 3, 4, 5, 6, 7. Okay, so we get this string. Now we have to see if does this string lie in our language a or not. So let's count how many a's we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 a's and how many b's? 7 b's. So 11 and 7. So the number of a's and number of b's are not equal. So in our language, number of a's should be equal to number of b's. So this string does not lie in our language. Alright, this string does not lie in our language for case number 1. Now let's try the same thing for case number 2. Let me take x, y raised to I, z, and let me choose my I to be 2. So I have x, y square, z. And what is x? X contains 7 a's and 2 b's. 1, 2, 3, 4, 5, 6, 7, and 2 b's. And y. Y contains 4 b's. 1, 2, 3, 4. And I have y squared. That means I repeat y once more. 1, 2, 3, 4. And then z. Z is only 1 b. Now let's count how many a's and b's we have. We have 1, 2, 3, 4, 5, 6, 7 a's and how many 11 equals z. And I choose my I to be 2. Now let's see. Here x is 1, 2, 3, 4, 5 a's. 1, 2, 3, 4, 5. And y contains 2 a's and 2 b's. 2 a's, 2 b's. And repeat y once more. 2a, 2b. And then z. Z contains 1, 2, 3, 4, 5 b's. 1, 2, 3, 4, 5. So here, if you before we count, you can see that this does not follow the pattern a raised to n, b raised to n. See here we have a's and followed by 2 b's, and again there are a's and b's. So it is not following this pattern. So this also does not lie in our language. So we prove that when we take x, y, I, z, and taking I to be 2, all this does not lie in our language. So let's return back to our rules once more. So that now this satisfies all three pumping conditions at the same time. So we saw that this condition cannot be satisfied. So we are taking x, y raised to I, z, and we show that it does not belong to A. So it will be regular only when it belongs to A. So we have shown that it does not belong to A, hence it is not regular. So we also show that this condition is also satisfied. C condition number 3 says that length of x, y should be less than or equal to p. Let us see if that was satisfying. Length of x, y should be less than or equal to p. And now case p was 7. So let's see in case number 1, what is the length of x and y together? 1, 2, 3, 4, 5, 6. So case number 1 satisfies because 6 is less than or equal to 7. What about case number 2, x and y? X contains only 1, 2, 3, 4, 5, 6, 7, 8, 9, and how y? 10, 11, 12, 13. So 13 is not less than or equal to 7. So it's not satisfied here. And if you check here, here also x and y together 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it's 9. So 9 is not less than or equal to 7. Even the first condition also is not satisfied. So we saw that those conditions cannot be satisfied when we divide our s into 3 parts x, y, and z. If you see the rules, we see that once we satisfy all these conditions cannot be satisfied, then s cannot be pumped. That is a contradiction to our assumption that A is regular. So we assume A is regular, but since it's not satisfying these conditions, it shows that it cannot be pumped, and hence we have proved that the language A is not regular using pumping lemma. So I will demonstrate to you. We will practice more examples, and I will also be discussing some more examples of this in the coming lectures. Thank you for watching. See you in the next one. In this lecture, we will be seeing another example where we will be proving that a given language is not regular using pumping lemma. I have discussed the steps in the last 2 lectures in detail, so in this one we will not be discussing steps in detail anymore. Okay, so let's see the language that we are given. The language that we are given is this one, A, which is equal to y for all y belongs to 0, 1 star. 0, 1 star means the set of all strings that can be formed using the symbols 0 and 1. So let us first understand why this language is not regular. So this language is of the form y, which means that the first part of the string should be same as the second part of the string. So any string whose first half is equal to the second half will line this language. For example, let me take this first y to be 0, 1. So if my first y is 0, 1, then the second y should also be 0, 1. So we see that the first half of the string is equal to the second half. That is the language assumes that we accepted by this language. Now why this is not regular is because in order to repeat the first part exactly in the second part, you need to remember what was the first part. In order to remember what was the first part, you need to have memory. So only if you store the first part in memory, then you can repeat it exactly in the second part. But we know that finite state machines has a very limited memory, and this kind of thing cannot be stored in its memory. So since this kind of language here requires memory, it cannot be designed using finite state machines. And if it cannot be designed using finite state machines, that means it is not a regular language. So I will understand why it is not regular. Now that is a critical knowledge that we have, but we need to prove using pumping lemma. Okay, so let's see how we can do it. So for the proof, what we'll do is we'll first assume that A is regular. So assume that A is regular. So this is how we do it. We'll first assume that it is regular, and from the steps that we will follow, we will derive a conclusion that will contradict with our assumption, and from the contradiction, we will prove that it is not regular. So first we assume that it is regular. So we already discussed if A is a regular language, then it must have a pumping length. It must have a pumping length. And let me call that pumping length to be p in this case. Alright, so I call the pumping length p, and now what I'll do is I will choose a string s from this language. Okay, and I can choose a string. Now let me choose a string like this. For example, 0 raised to p 1, 0 raised to p 1, where p is my pumping length. Now we see that this means that the string contains p number of zeros followed by 1, and then again p number of zeros followed by 1. So we see that the first half and the second half are exactly similar. So it lies in this language A. Okay, so once you have chosen the string s, the next thing that you have to do is you have to divide this s into 3 parts x, y, and z. Now that's what we have to do. So as we divide into 3 parts x, y, and z, let me take an example. Let's say that for example I said that my pumping length p is equal to 7. Okay, so if pumping length p is equal to 7, then let me form a string using this s and p whose value is equal to 7. So I will have 1, 2, 3, 4, 5, 6, 7 zeros, and then so on. And again, 1, 2, 3, 4, 5, 6, 7 followed by a 1. Okay, so this is the string that we have. And now I will divide this into x, y, and z. So most important is our y. So let me say that this 4 zeros over here, this is my y, and these 2 zeros is our. In this lecture, we will be studying about regular grammar. So before we start with regular grammar, let's try to understand what is a grammar. So in normal human languages, what is the use of grammar? Why do we use grammar? So grammar is actually a set of rules that we use for proper conversation with each other. So in the same way, for writing computer languages also, there is a mathematical model of grammar which is used to write the languages in the correct way. So Noam Chomsky, he gave a mathematical model of grammar which is effective for writing computer languages. So this person Noam Chomsky, he gave a mathematical model of grammar which can be used for writing computer languages. And according to Noam Chomsky, there are 4 types of grammars which we will discuss here. So the types of grammar that we have according to Noam Chomsky are type 0 grammar, type 1 grammar, type 2, and type 3 grammars. So we will discuss them starting from the bottom. So first let's see type 3 grammar. So in type 3 grammar, the grammar that is accepted are regular grammar, which we will be studying in this lecture, and the language accepted by this type 3 grammar are regular languages, which we have already studied in the previous lectures. And then the automaton that is used for designing this kind of grammar, this type 3 grammar, is finite state automaton. That is a finite state machines of finite automaton, which we have already studied in the previous lectures. Okay, and then we have type 2 grammar, in which the grammar accepted are context free grammar, and the language accepted by type 2 grammar are context free languages, which we will be studying in the following lectures. And then the automaton that is used for designing this is the pushdown automaton. Alright, and then we have type 1 grammar, in which the grammar accepted is context sensitive grammar, and then the language accepted by this is context sensitive language, and then the automaton that is used for designing this is the linear rounded automaton. And then we have type 0 grammar, in which the grammar accepted are unrestricted grammar, and the language accepted by this is the recursively enumerable language, and then the automaton that is used for designing this is the Turing machine. Okay, so these are the types of grammar that we have according to Noam Chomsky's classification, and we will be starting with regular grammar, which we will be discussing in this lecture. So first, let us see how can we define grammar, and then we will come to regular grammar. Okay, so here we will see how can we formally describe grammar. So a grammar G can be formally described using 4 tuples given as G equal to B, T, S, and P. So a grammar G can be defined using 4 tuples which are B, T, S, and P, and let's see what does this tuples mean. Where V equal to a set of variables or non-terminal symbols. So V is a set of variables or non-terminal symbols, and T is a set of terminal symbols, and S is a start symbol, and P is a production rule for terminals and non-terminals. Okay, so B, T, and S are easy to understand, but let's try to understand what is P. P. P is a production rule. A production rule has the form alpha tends to beta or alpha gives beta, where alpha and beta are strings on B union D. That means it can belong to the set of non-terminal symbols and terminal symbols, and at least one symbol of alpha belongs to B, which is a set of non-terminal symbols. So don't worry if it is a bit confusing, it will become clear when we take the example. So here we have an example given. We have a grammar G, and then it is equal to, and we have a set of symbols here S, A, B. Then we again have small a, b, s, and then this production rule. So let's try to understand this example grammar which is given here, and let us try to see what are the tuples in this. So we have the first tuple which is V, which is a set of variables of non-terminal symbols. So here it is S, A, and B. S, A, B. These are the variables of the set of non-terminal symbols. And then we have T, which is a set of terminal symbols, which are A and B. A and B are the terminal symbols. And then we have start symbol S, which is equal to S itself here. Start symbol is given by S. And then we have a production rule P, which is given by this. So the production rule is given like this. S gives A, B, and A gives small a, and B gives small b. So this is the production rule of this grammar. Now let us try to take an example and see some strings that can be formed using this grammar that is given here. So we have to look at the production rules over here. So our starting symbol is S. So I take S, and I can say that S gives AB from this production rule. S gives AB. So S gives AB, and then we also have in the production rule that A gives small a. So instead of this big letter A, I can write small a because A gives small a, and then this B I can write as it is, and then this B also we see that it gives small b. So this A as it is, and instead of this B I can write small b by this production rule. So we get a string AB. Now this string AB is something that is designed using this grammar. So this is how we will design our strings, or we will find our strings that will be accepted by certain grammars. Okay, so I hope that made the grammar clear to us. So that is clear. Let's go to the next part, that is regular grammar, which we will be discussing now. Okay, now let's come to regular grammar. So regular grammar, it is of two types. It can be divided into two types. The first one is right linear grammar, and the other one is left linear grammar. So let's see what is the meaning of right linear grammar and left linear grammar. Let's try to find out the difference between them. So a grammar is said to be right linear if all productions are of the form A gives xb, and A also gives x, where A and B belongs to V, which is a set of non-terminal symbols, and x belongs to T, which is a set of terminal symbols. So if you have a grammar and the productions rules are of this form, here, if you look here, you see that x is a terminal symbol and B is a non-terminal symbol. Now, if the non-terminal symbol lies to the right of the terminal symbol, then it is said to be a right linear grammar. So here we see that x is a terminal symbol and B, which is a non-terminal symbol, lies to the right side of x, the terminal symbol. So it is a right linear grammar. And then left linear grammar is just the opposite of that. I hope you know what is the difference. A grammar is said to be left linear if all productions are of the form A gives bx and A gives x, where A belongs to set of non-terminals and x belongs to set of terminal symbols. So here we see that x is a terminal symbol and B, which is a non-terminal symbol, lies to the left of the terminal symbol, which is x. So this kind of grammars which have this kind of production rules are said to be left linear grammar. So let's take a simple example to understand it right away. So here let me take an example where I have a grammar whose production rule is of the form S gives A, B, S, and also B, let's say. So S gives A, B, S, and also B. So here A and B are the terminal symbols, and S is the non-terminal symbol. So here we see that S, which is the non-terminal symbol, lies to the right of A and B, which is the terminal symbol. So this is a right linear grammar. So this is right linear. Now if I have another grammar S, which has a version rule of the form S gives S, B, B, and also B. So here B is the terminal symbol and S is the non-terminal symbol, and we see that the non-terminal symbol S lies to the left of the terminal symbols B. So this is a left linear grammar. So this is how you identify right linear grammars and left linear grammars, and this is the difference between them. So I hope this made us the concept of right linear grammar and left linear grammar clear to us, which are the types of regular grammar, and we also understood what is the meaning of grammar, and we also saw the types of grammar according to Noam Chomsky's classification. So I hope this was helpful to you. Thank you for watching, and see you in the next one. In the last lecture, we have studied about grammars. We have also seen some types of grammars, and we have also seen how grammars are formally defined or described. So in this lecture, we will be seeing about derivations from a grammar. So what do we mean by derivations from a grammar? So it says here that the set of all strings that can be derived from a grammar is said to be the language generated from that grammar. So suppose we have a grammar given, and all the sets of strings that can be derived from that grammar, that is known as the language generated from that grammar. Okay, so let's see a single example of that. Okay, so here we have an example given. Consider the grammar G1. We have a grammar G1 given here, and here in the grammar G1, S and A, these are the non-terminal symbols of the variables, and A and B are the terminal symbols, and S is the start symbol, and we have a production rule given like this: S gives A, A, B, A gives A, 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 B, and A gives epsilon. Okay, so let's try to see some strings that can be generated from this grammar G1. So let me start from the start symbol that is S, and from S I can get A, A, B, small a, capital A, and then B. So this is using the production rule. S gives A, A, B. Okay, now let's try to expand this. We have A, A, B here, and now we have one production rule which says A, A gives A, 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 B. So this A, A over here, it can be expanded and written as A, 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 B, A, 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 B. So I expanded this part, and I have this B remaining over here. So this is by the production rule which says A, A gives A, 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 B. Okay, now let's further expand this. From here again, by the same production rule, I can take this A from here and let me expand it. This A can be written as A, A, B, A, 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 B, and this B will be written as this, and this B also will be written as this. So this is also by the production rule, which is the same as above. A gives A, 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 B. Okay, and now I would like to further expand this. Here I have this A over here, and instead of A, I can write epsilon. That means I can replace with